Okay, cool. Okay, this is just for review. So, yeah, derivatives I feel pretty good on. I'll get to this back in a second, but I feel like your derivatives should be solid. And so if I wanted to quiz on derivative or derivative technique later in the week, maybe Thursday, you should be good. I'll nail that down for sure by tomorrow. But I'm feeling like Thursday derivative technique quiz, maybe a little longer than the limit quiz. All right. Anybody absent Friday and not take the limit quiz? Cool. It was pretty easy. Most people did well or made a sort of mistake, but they didn't seem like there were conceptual issues. Here we go. Let's go with antiderivatives. When you take an antiderivative, you can always check your answer by deriving. You're taking a derivative, seeing if you get right back to your antiderivative. So the anti-power rule, for example, instead of taking a derivative and multiplying by the power and reducing by 1, and an antiderivative, you divide by the power and raise it by 1. Yeah? So, for example, x to the second is, antiderivative of x to the second is 1/3 x to the third, yay? Just like in normal differential calculus, I strongly recommend rewrites. So, for example, if I had 1 over root x, you might at least mentally think of that as a power of -1/2 before you do your power rule thing, yay? Yes. Log of absolute value of x. This was a bit of a misconception on our homework, so I want to review a real quick idea here. This and this. There's a homework where people were confusing those two. The second one, what does the graph look like? It wants to be loggy, like this, but y's are never negative, so the part that was negative gets flipped up, yeah? Cool. What does this look like? Yeah, for positive x's, there is no change. And for negative x's, which would normally not be allowed, now they are allowed. So it increases the domain and allows for negative. All right, then. So with that in mind, doesn't it make sense that the derivative is very steep and then flatter and flatter and flatter? So the derivative looks like that. And this is negative slope and starting very flat and getting steeper and steeper as we go this way. So that. My point, though, is this. If you anti-differentiate 1 over x, you don't know if positive x's or negative x's were allowed to begin with. So when you go backwards, you have to think, well, I want to be as inclusive as possible. So that's why the absolute value is there, so as to allow for negatives in the original, okay? So don't forget the absolute value. E to the x is the easiest of all. Have you anti-differentiated a to the x, like 2 to the x? Yes. You have. You did get to that last year. Yes. Okay, good. We'll review that at this. That's about set 70-ish, 71-ish. But we'll review that soon. These tend to get people. The antiderivative of sine is negative cosine, because remember, cosine's derivative is negative, so the antiderivative of sine is negative. Cosine of sine, you get the idea. Tangent, how can this be found? It says it can be found by use of. I told you that. What is that? How would you do it? Sine over cosine, yeah. If you rewrite tangent as sine over cosine, then let u equal, do you let u equal sine or cosine? Let u equal cosine. Oops. Du is negative sine of x dx. Do you agree you've got a straight negative in there, so you'd probably move it over. And then with u sub, it would become negative du over u. The antiderivative of which is negative natural log of the absolute value of u plus c. And if you then sub back negative natural log of cosine plus c. It's more common, though, that you'd see the antiderivative of tangent is log of secant. Where does that come from? I don't see secant in there. How does this become log of secant? Yes? Yeah. So log rows with log rows, if you put that negative up there, so it was to the negative first, cosine to the negative first is 1 over cosine that secant. That's the more common form. Cool. Cotangent is log of sine. Again, if you don't remember it, you can get it by u sub. Oops. Have you, oh yeah. Let's go, so would you, I didn't put these in. Would you drop these in here? What about secant tangent? What's that equal to? Secant, because that is the derivative of secant. So C, what about a negative cosecant cotangent? Negative cosecant. Sorry, I meant to have those in there. There are a lot of antiderivatives you haven't seen yet that we will cover later this semester. Did you do inverse trig antiderivatives? Okay, and then this is a classic. We'll get that later. But all right, now let's talk. I think antiderivative rules. First of all, is the log of something with a, or sorry, the log. The antiderivative of something with a coefficient. Is it okay to pull out that coefficient out front and just focus on the function? It is okay. Is it okay to, in integrating a sum, break it into a sum of integrals? Yes. Is it okay in integrating a product, f and g, to integrate each part separately? Is that a thing? No, it is not a thing. That is 100% true. Just like the product rule doesn't work that way in derivatives, the anti-product rule doesn't work that way. You cannot do that. There are other rules, same with division, by the way, and subtraction. They follow addition and division, multiplication. All right, when dealing with an improper fraction, this is often not taught. It's not taught in our book for sure, and so I just want to make sure you miscounted brought it in or you know it now. When you're dealing with an improper fraction, what's the technique? Now, improper fraction means, in algebra terms, mean greater power in the numerator, greater or equal power in the numerator. What do you do? Yes? Separate them, yeah. So 3x plus 1 plus 2 over x dx, and then you integrate each term by term, yeah? Now that usually goes fine, and I think our textbook did do that, but what if you have something like this? What must you do? Okay, put off to the side, divide first. You must divide first. So, that, can I synthetically divide if the divisor is linear? You can. Do you feel more comfortable synthetically dividing or actual long division? Synthetic. Okay, what goes in the box? 1 or negative 1? Negative 1. 3, 1, and 2. And when you divide, the algorithm says 3, multiply, add, multiply, add. So super. What is that problem equivalent to? 3x squared. 3x squared. No, not squared dummy. Thank you. I don't think you said the dummy part. 3x minus 2 plus 4 over x plus 1. And then you integrate, let's just make sure we're full. What's the antiderivative of 3x? 3 halves x squared minus 2x plus 4 natural log of the absolute value of x plus 1 plus 3c. All right? What if it is uglier? 3x squared plus x plus 2 divided by x squared plus 1. Yeah, you might be able to, it might be good. Okay? All right, we'll see how it goes. So, can you use synthetic division if it's a nonlinear divisor? So, you must long divide x squared plus no x plus 1 into 3x squared plus x plus 2 and divide x squared. Let's look at the first term into the first term. How many times does x squared go into 3x squared? 3 times. Then what do I do? Then you multiply. You remember how to long divide? Okay. Well, you multiply the divisor by that and write it here. 3x squared plus 0x plus 3. And then you switch signs or change signs and draw the line. No x squareds, x minus 1, yeah? Okay, so plus x minus 1 over x squared plus 1. This is a humdinger. I'll bet you're glad we did this together because I hope there's one on tonight's homework. So we're going to integrate 3 plus x minus 1 over x squared plus 1. Are you keeping up or hold on a minute? Okay. All right. I'll do the first part. The antiderivative of 3 is 3x. Now you do the second part. Go. What's the technique or the approach to the second? Okay, use sub is a good idea. You will have to use sub, but you'll have to do something first. Okay. So if you're use subbing right away, then you're not going to. What must you do first? This needs to be x over x squared plus 1 and 1 over x squared plus 1 because the two approaches are very different. You must split. All right, so 3x is fine plus. Now, the second term, what's the approach? U sub. Now, what is the u? X squared plus 1. What's the du? 2x dx, but you don't have an x, 2x dx, you have a x dx. So what do you do about the 2? Divide. So something like that. So that when it gets replaced, what does the new integral become? 1/2 du over u, the antiderivative of which is 1/2 natural log of absolute value of u, and what does u get replaced back by? X squared plus 1, so 3x plus. Okay, now the last guy. Don't lose that negative up front. What is that? It's our tangent. Okay, that's a memorized derivative. That's our tangent. Obviously, it's been a long summer, so you might not have that memorized anymore, but you will again. And so that is Donner's minus arc tangent of x plus c. And that's pretty close. I pulled that from a college exam from last year. Okay? Okay, so my point then is if you get an improper fraction, you have to divide first, and that can be easy if it's just a single variable. It can be a little harder, synthetic division, or it can be just downright atrocious. All right, moving on. U sub, which we just covered, and it's kind of the anti-chain rule. When you do a derivative by chain rule, don't you get a product where one's the derivative of the inside of the other, right? So when you see an integral where one, it's a product, and one is kind of like the derivative of the inside of the other, like this. One term of a product is like the derivative of the inside of the other. That screams U sub. Okay, so, oops, I already have a definite integral problem in here. I obviously got some of these in poor order, but that's okay. So, let's say we look at this guy here. I will get to definite integrals a little later, but I guess I'm going to have to get it now. So it says here that u is to be 2 minus x. So this then, in the square root, will become the square root of u. Okay. Now, with that domino effect, everything else is going to change, but I'm going to write myself a note here. U is the inside of the composite function. When you go to choose u, you say, all right, what's the function within a function? And the inside is what the u is. So you can see that x is just a plain old thing. But root of 2 minus x, that's a function within a function. The u is the inside of that function. So u is 2 minus x, that's how they choose that. In this case, they told you. So what does x become then? If u is 2 minus x, then x is 2 minus u. Okay? That's been sub 4, that's been sub 4. What about dx? Well, I would need to take a derivative. Isn't dx equal to? If I take the derivative of x equals 2 minus u, isn't dx equal to negative du? Okay, so I could sub in for dx with a negative du. What about the limits? Do they change? Yes. Yes, they must change. So, if, based on the fact that u is 2 minus x, when x is 1, what's u equal to? 1. When x is 3, u is 2 minus 3, so negative 1. Do I put the negative 1 on the bottom and the 1 on the top because I want it to go from lesser to greater? Or is it 1 on the bottom and negative 1's on the top? Because, doggone it, I don't get to change the order unless I do something else. So, which is it? 1 on the bottom or 1 on the top?
1 on the bottom.
1 on the bottom. When you put in 1, you got out 1, and when you put in 3, you got negative 1. All right? Looking at their choices, I don't see that as a choice. So, what is a rule for definite integrals we're going to use? Yeah, when you switch these limits of integration, it is negate, yeah? So if I change those from negative 1 to 1, I negate. I don't know where they negated, but I would imagine they took off the negative on the du. Yeah? Leaving you at 2 minus u root u du. So what do I conclude? My answer is
N.
N?
E.
Oh, you're cooking me out. All right. Do we agree? Try the next one, please. Try the next one. Wandering in the night. What take a chance? Oops. Maybe showing us before the night is through. What are we thinking? D as in dog? Yay, we win. Okay, if that did not go well, execute or figure out your mistake and go from there. Last but not least, is this next on the notes? Did I record these properly? We're good? Yeah. Okay, integration by parts, also known as ultraviolet voodoo. All right, ultraviolet voodoo. That's the exchange. Ultraviolet voodoo is the integral. Obviously, you need to remember the subtraction and the integral sign, but then you're good. All right, where does it come from? Oh, they just told me. She told you where it came from. Do you remember? Okay, it comes from rearranging the product rule of a derivative. Imagine, if you would, you had uv, and you took the derivative with respect to self. Okay? So, by product rule, what is the derivative? First stays the same. U times the derivative of the second, dv, plus second stays the same, v times the derivative of the first, du. Make sure your u's and v's are super different looking. The v's super pointy so you don't get them all confused, which is very common. All right? Now then, if you rearrange a wee bit, so I just keep this here and move this over, then I would get something like the derivative of the product minus v du equals u dv. Now, calculus behaves like all other math functions. Whatever you do to one side, you must do to the other. So if I were to then take the antiderivative of both sides, now at this point you're thinking, what a waste of time. I took the derivative, now I'm taking the antiderivative. What's the point? Well, hang on for a second. This first one, what's the antiderivative of the derivative of uv? uv. And what is the antiderivative of that? Well, it's kind of hard to say without knowing, so I'm going to call it the antiderivative of voodoo. And the result is this. Now, why you would do all that is because sometimes you get a case that's u sub e like that. Do you agree that's u sub e? Because you have a product and one's the derivative of the other. U sub. But sometimes you get one that's not u sub e. That's a product, but that is not the derivative of the other. You could u sub that all day long and it will never work. It's not a u sub problem because it's not a chain rule derivative. So the idea was some genius on the line thought, oh, shoot, you get products two different times. You get derivatives that products two different times. One's chain rule, but the other is product rule. So to deal with a case like this, they said, let's start with the product rule, which has a product in it, and rearrange stuff, and that's when they got this. So when is it used? When you have a product, but one is not the derivative of the other. Would you write yourself a quick note? Be careful. This, I just said use it when you have a product. And people look at natural log and think, well, that's not a product. Well, yeah, it is a product. Because natural log is a thing, and dx is a thing. Students are tempted to say, dx, that doesn't even exist. No, that's a thing, okay? And so this is a product. And if you go to find the antiderivative of that, it's ultraviolet voodoo. You've got to use ultraviolet voodoo. Same with this. Arctangent. That's ultraviolet voodoo. So if you kind of need to think outside the box. Your first thing is not typically to think ultraviolet voodoo here because it doesn't feel like a product, but remember dx is a thing. It's a factor, and it does behave like a product, right? In terms of choosing u, the best u is log. The next best is inverse trig. Then polynomial, like x to the power or root. Then we're starting to get into terrible territory. Exponential and trig are the worst. So when you get an example of something like, let's go x cubed log of x. U sub is the most useful, so that should be your first, can I go for it? So is this a U sub problem? It is not a U sub problem, right? So instead I feel like, okay, it's a product, maybe I can use the integration by parts, so ultraviolet voodoo idea. You follow me? So when you go to do this, you need to, I guess, have in your mind the blueprint. The whole idea of ultraviolet voodoo is if you have an integral of two things, it's ultraviolet minus voodoo. And to use it, you need to figure out in this problem what's u and what's dv. That goes up to here. What's the best u you can do? Natural log. So you want to let u be the natural log. According to the rest of the blueprint, whatever's left over then is dv. So what's dv? Well, I already got the natural log, so everything else is dv. So what's dv? X cubed dx. All right, now we're going to do a little baby integration and differentiation in our head. First, the baby derivative. If u is log of x, then du is 1 over x dx. And v, if dv is x cubed, then v is the antiderivative of x cubed, which is 4th x to the 4th. All right. Now, we're hoping to take a step forward with our ultraviolet voodoo. What's uv? One fourth x to the 4th natural log of x, and obviously the order doesn't matter if you wrote it in the log first, that's fine. The antiderivative of, what's v?
1/4 x.
And what's du? 1 over x dx. With a little bit of cleanup, 1/4 x to the 4th log of x minus 1/4 x cubed dx. Write yourself a note here. If the new integral is not better, then you made a mistake. The whole idea is to exchange an ugly integral for one that's better. And if that doesn't happen, then you must have chosen u badly. Okay, so now we're ready to integrate 1/4 x to the 4th natural log of x minus, what is the antiderivative of 1/4 x cubed? 1/16 x to the 4th plus c some more. My life depends on getting that right. How can I check it? Take the derivative and hopefully it should be x cubed natural log of x. Sweet. Okay. Is that? No, that's not all. All right. Those, with the exception of 1 and 2, those were indefinite integrals. Definite integrals have far more meaning, which we'll get into soon. For now, we'll just get through the very most basic level of the fundamental theorem, which is how to do it. Not what does it mean, but how to do it. So, the fundamental theorem of calculus, one of the greatest ideas of all mankind, is that if you have a definite integral of a function, you can first find the antiderivative, which most books call capital F. and then evaluate at the upper minus the lower. Upper limit of integration minus the lower limit of integration. That's not the meaning of it, the why of it, and all that stuff we'll talk about this week. For now, it's just the logistics. What do? You take an antiderivative and at the upper minus the lower. Would you try that definite integral, please? Evaluate that definite integral without a calculator. And let's verify that this is coming back to you. What did you get? A, B, C, D, E, or not done yet? Oh, sorry. Okay, are you feeling A? Good. Are you feeling D? All right. I agree with D. If you do not agree with D, then either I made a mistake or you made a mistake. My money's on you. All right, are we good? Is that all? Wow, that was so easy. All righty then. Would you grab Friday's homework? And let's talk about that homework. I've got to check off the box that you made. Or I will check the box off by the end of the day, but it needs to be made. If you felt like, does he really want me to make a box? The answer is yes, I do. Now, it's a box. If no denying, that's a box. Here, if you need to show me later, I will see it later. I need to, I'm going to check it now. So, no, you do not have to put your name on the box. Alright, then where's his Hi. What are you doing? Oh, you're doing pictures. Oh, I thought you were showing me on. Hi. Let's get, ooh, you got your white on there, right there. Right there. Right on. You never know, maybe it's the right box. No. Oh, well, I appreciate you. Let's see, you're on. Alright. Wow, that's some box. You put it in your backpack? Okay, there you go. You are cool. Alright. Okay. Oh.
It's my airplane.
You're cold. You rip it, you end up like me with no butts.
Or like mud. Absolute dirt.
So you're cold.
Wait, why did you work? Like we have to change later. Too many times when I finished them because there were holes in the box. I created the situation for everything.
I need another piece of paper. Scratch paper here.
Good job, son.
Yours also will be decorated with trigonometry.
Thank you. You have to solve it.
No, I'll just type it. That way you'll never know.
That's a horrible box, but you can't check.
That is something. Ella. No,
That's
I am
great.
good. Of course, maybe I should collect it so your house can
Wait, can I just get rid of this box?
What? Will you put them all on that little table over there?
What?
Oh, I guess it's a birthday. Yeah, just open that little table over there. So I know just I
Yeah. Do we need to put our name on it?
Sure, throw your initials on, your name on it. Right here. Here we go. Okay.
Now my name's on my box.
Okay, cool. All right. Now I need to.
The loading time, I did not do. I brought it up into the rear.
Wait a second, that doesn't work. Too lazy to do easier. I don't have my review aid. That's me. My review aid is garbage. Shoot. So I do not have my review 8 key. Hang on with 1 minute. Do. Review 8. Sorry. Okay. Here we go. Oh, you're so quiet all of a sudden. That'll be stuck in your head. Okay. All right. Lo siento, mijos. Okay. All right. I'm going to have to rely on you because I left my key at home. So, where did you say it was concave up? On what interval? Somebody shout it out. Negative infinity to 1? And down then is 1 to infinity? And were there any inflection points? Must have been an inflection point if I can see that it went from concave up to concave down. So there's an inflection point at x equal 1. Actually, let's go I didn't say, oh, it said coordinates.
1, 2.
So 1, 2, why? Justify, because
Because
It changes sign.
it,
double,
double, no F, there's no F. Y double changes sign at that point. Okay. Let's go here. This one actually requires a little more. Minus 12x squared. First or second derivative test, you still have to pause here. And did you get critical numbers at 0 and 3? Yes. Okay. Now it says find the x where all relative extreme occur using the second derivative test if possible. First derivative test otherwise. So second derivative is 12x squared minus 24x. If I take the second derivative, do I sign test the second derivative, or do I test the second derivative at those critical points? At the critical points. Y double at 0 is 0. What kind of concavity do I have then? None. And so what does the second derivative test tell me? Nothing. Second derivative test fails. If the second derivative test has no sign, the second derivative doesn't tell you what you need it to tell you, which is concave up or concave down. Second derivative test fails. What about second derivative at 3? You get something like positive. Up me here, people. I feel like it is positive. It is positive. And so that means the graph, the original graph, would be flat because the first derivative was 0 and concave up. So the graph must have a min. So let's do the conclusion for 3 right now with the second derivative. Then we'll deal with 0 in a second. All right. So the curve, or y, whatever you want to call it, has a local min at where? X equal 3 because y? Y prime at 3 is 0, and second derivative is positive or greater than 0. Do I need both of those pieces of information, or is just the second derivative enough? Both. If the second derivative positive is not enough, there's a lot of concave up points that are not extrema. It has to be flat with concave up. The combination is a min. All right. Uh-oh. Sorry about that. Okay, so the second derivative test failed at 0, so that means I have to go back and look at x equals 0 with the first derivative test. When I first derivative test, do I look at 0 or around 0? Around 0. First derivative test is interval testing, and so I test and I get something like positive before, no, negative before 0 and negative after 0. Oui. So it was decreasing before 0, then it went flat, but then it went back to decreasing, and then we have a min. So what's going on at 0? Inflection point. There is no extrema, and so to answer the question, there is no extrema. I guess it's just at x equals 3. Are we cool? Okay. Our interest, 200 feet of fencing. What did you get for? Actually, it kind of depends on what your picture looks like. Did you call this x, y, height what? Y. All right, that makes no sense to me. Y. It's going up and down, you crazy people. X is the whole thing, or X is one of these things? There's not a right or a wrong here. It's just kind of what did you do? Okay, depends. All right. Did you do? I'm going to say this. Okay. If you do that, then when you do optimization, you start with what you're trying to optimize. Am I trying to optimize the perimeter or the area? The area. And the area for that is xy or 2xy. It's fine either way, because either way, if you maximize xy, you've got it max. If you maximize 2xy, you've got it max. So it doesn't matter if you did xy or 2xy. That's not an issue. Wouldn't you agree, though, that that's 3 variables, and that's bad? We want to get 2. So what do I do to get it down to 2? Substitute. So what is the other relationship? 200 equals 3y plus 4x, and solve it for one or the other, doesn't really matter. Let's say I solve it for, did you solve for x or y? X, all right. X is 200 minus 3y each over 4. So x is something like 50 minus 3/4 y, if you like. So you get, when you distribute, you get 50y minus 3/4 y squared. Find a prime as area changes. Is area changing with time or with changes in x or y? Is this a related rates problem? Are we changing with time? No, there's no time component. Okay, it's as, so this would be dA dy if I use good Leibniz notation. So that said, what is your horizontal and your vertical? Did you get something like 60 over 3 or 200 over 3 or something like that? All right, I guess I'll just continue on. So, did you get 50 minus 3/2 y for a derivative, and 50 equals 3/2 y, so y is 100/3. Did you get the long side is 100/3?
Yes.
And what does that leave for the other guy? 25 for each x. Okay, and I didn't check that that's maximum, but I could prove. All right, from 0 to, from A to B, what's the graph doing?
Decreasing, concave up.
Decreasing concave up. At B rather, what's, oops. At B, what's it doing? Give myself enough time. Sorry. B, A, decreasing concave up. At B, what's it doing? Flat concave up. From B to 0, what's it doing? Increasing concave up. At 0, is it flat or still sloping up? Sloping up. And what is the second derivative going on at 0? The inflection point after that, it's increasing concave down. So did you give it something like that?
Yes.
Okay. Find all values at which f attains a relative min. I bet this will get you. I'll tell you what, we're going to have to go. Is it all about right? Yeah. Okay. I'll finish going over this tomorrow. So I'll give it a quick look for completed it tonight, and we'll finish going over it tomorrow. So make sure I did it at the end of the day. I'll get it back to you tomorrow. We'll talk. Okay? How about a beautiful, lovely day?
I get the first one.